Have you ever wondered why prime numbers are so important in mathematics? Well, brace yourselves for a journey through the world of prime numbers. These special numbers, defined as natural numbers greater than 1 that have only 2 divisors, 1 and itself, hold a position of paramount importance in the realm of mathematics. They can't be evenly divided by any other number, making them the loners of the number world. But don't let their simplicity fool you. Underneath this straightforward definition lies a world teeming with complexity and richness. Prime numbers are infinite, and though they become less frequent as we journey through the line of natural numbers, their significance never fades. They are fundamental elements in number theory, with significant applications in fields from cryptography to data science. So now that we know what prime numbers are, let's delve deeper into their fascinating world. The simplicity of prime numbers belies their complexity. You see, they are not just numbers that have only 2 divisors, 1 in themselves. They are part of an infinite sequence that holds a labyrinth of intricacies and mysteries. The line of prime numbers extends indefinitely, a never-ending chain of special integers. But the fascinating part is not just their infinity, it's the way they behave, the way they appear as we traverse the vast landscape of natural numbers. Now imagine this landscape as a dotted line, where each dot represents a natural number. As we move from left to right, we mark the prime numbers. In the beginning, they seem to appear quite frequently, but as we progress, they become less and less frequent. This seemingly random distribution of prime numbers is one of their most enigmatic characteristics. But let's dive deeper. Let's talk about Fermat's prime number theorem. This theorem, named after the brilliant French mathematician Pierre de Fermat, states that there are infinitely many prime numbers. It's a simple statement, but one that anchors the unlimited potential of prime numbers. No matter how far we journey into the universe of integers, we will always encounter more prime numbers. Their infinity is not just a theoretical concept, it's a mathematical reality, proven by Fermat's theorem. But why does this matter? Why should we care about these unique numbers? Well, prime numbers are not just mathematical curiosities. They are fundamental building blocks of all natural numbers. Without them, our understanding of numbers and, by extension, the world around us, would be incomplete. Prime numbers are not just an infinite sequence, they are a fascinating mathematical marvel. Their simplicity conceals a world of complexity, a world that mathematicians have been exploring for centuries. And yet, despite all the progress, prime numbers continue to intrigue us, to challenge us, to lead us into new realms of mathematical discovery. But prime numbers are not just academically interesting, they have practical applications too. Indeed, the significance of prime numbers extends far beyond the realm of pure number theory. They play a pivotal role in various fields such as cryptography, graph theory, computing, and data science. Take cryptography, for instance. In the world of digital security, prime numbers are considered the bedrock of many encryption algorithms. These algorithms are what keep our digital data safe from prying eyes. They're used in everything from securing our online banking transactions to protecting sensitive government information. The RSA algorithm, a widely used public key crypto system, relies heavily on the properties of prime numbers. Here's a simplified version of how it works. The RSA algorithm begins by selecting 2 large prime numbers. These numbers are then multiplied together, and the resulting product forms the basis of the public and private keys used in the encryption and decryption process. The security of the RSA algorithm lies in the fact that, while it's relatively easy to multiply 2 large prime numbers together, it's extraordinarily difficult to do the reverse, that is, to factor a large number into its prime components. This asymmetry is what makes RSA and other similar algorithms secure. Prime numbers also play a significant role in graph theory and computing. In graph theory, prime numbers can be used to optimize network routing and data structure organization. In computing, they're used in hash functions and random number generation, among other things. In the field of data science, prime numbers can be used in various ways. For example, they can be used to reduce the dimensionality of high-dimensional data, a technique known as prime number coding. So you see, prime numbers aren't just an abstract mathematical concept. They're a fundamental part of many of the technologies that we use every day. They help to keep our digital lives secure, and they aid in the efficient operation of our technological infrastructure. Prime numbers, therefore, are at the heart of our digital security. Opening. Prime numbers also stand tall in the realm of fundamental mathematical theorems. Indeed, their importance is so profound that they play a key role in one of the cornerstones of number theory, the fundamental theorem of arithmetic. This theorem states that every natural number greater than 1 can be uniquely represented as a product of prime numbers. It's like saying that every word in the English language can be broken down into its constituent letters. Think about it. Let's take the number 28. It's not a prime number, right? But if we break it down, it can be expressed as 2 times 2 times 7, all of which are prime numbers. No matter how you slice it, you'll find that 28 is fundamentally composed of these primes. This theorem underscores the pivotal role of prime numbers in the structure of natural numbers. Just as atoms are the basic units of matter, prime numbers are the basic units of the natural number system. They are the indivisible entities from which all natural numbers are built. But the intrigue doesn't stop there. This theorem also asserts the uniqueness of this prime factorization. That is, a natural number can be expressed as a product of primes in one and only one way, disregarding the order of the factors. So, if we shuffle the prime factors of 28, we might get 7 times 2 times 2. But it's essentially the same factorization. In the grand tapestry of mathematics, prime numbers are the threads that weave together to form the intricate patterns of natural numbers. They are the hidden gears that drive the machinery of arithmetic. In essence, the fundamental theorem of arithmetic shines a spotlight on the unassuming prime numbers, elevating them from mere integers to the building blocks of the entire natural number system. It's like discovering that the humble bricks and mortar are the foundation of every architectural marvel. Closing, prime numbers thus are the building blocks of all natural numbers. Prime numbers have always been a source of intrigue. They hide within their simplicity a depth of complexity that keeps mathematicians on their toes. One such captivating facet is the concept of twin primes. Imagine 2 primes, standing side by side, separated by just one non-prime number, like 11 and 13 or 17 and 19. These pairs are what we call twin primes. Now here's where it gets even more interesting. Twin primes, like other primes, seem to become less frequent as we climb the number line. But unlike the overall decrease in prime number density, mathematicians are still unsure about the fate of twin primes. This uncertainty is wrapped up in what we call the twin prime conjecture. It's a hypothesis, a mathematical guess if you will, that suggests there are infinitely many twin primes out there, waiting to be discovered. This conjecture has been around for more than a century, and yet it remains one of the most intriguing unsolved problems in number theory. It's a mathematical cliffhanger that keeps us all on the edge of our seats. Despite numerous attempts and significant progress, a conclusive proof or disproof remains elusive. It's this kind of mystery that makes the world of prime numbers so fascinating. It's like a never-ending puzzle, a mathematical treasure hunt, where every discovery only leads to more questions. It's a testament to the depth and richness of prime numbers, their fundamental role in number theory, and their far-reaching implications in other fields. So the next time you come across a pair of twin primes, take a moment to appreciate the mystery they represent. Remember that behind their simple facade lies a century-old question that continues to challenge the best minds of our time. This ongoing mystery further fuels our fascination with prime numbers. So, prime numbers, simple yet complex, are a cornerstone of number theory. We've delved into the world of these unique numbers, exploring their intricate properties and the pivotal role they play in mathematics. We discovered their practical applications, stretching from cryptography to computing and data science, where they are instrumental in constructing secure algorithms and solving complex problems. We also touched on the fundamental theorems that highlight the importance of primes in the architecture of natural numbers. The fundamental theorem of arithmetic, for instance, underscores that every natural number greater than 1 can be uniquely represented as a product of primes. And let's not forget the captivating mystery that primes hold. The infinite sequence, the decreasing frequency, the twin prime conjecture, all continue to challenge and fascinate mathematicians around the globe. Prime numbers, while simply defined, hide a mathematical depth that continues to intrigue and inspire, making them a fertile ground for research and discovery.